Previously, we used an FEM simulation to deform an animated mesh. There are some functional benefits to this. However, this is not really the main reason to use FEM, as FEM will allow us to build up layers of simulation one upon each other. To do this, you'll be working with constraints. There are a number of constraints which you can use, but we're going to start with a straightforward example where we're going to take our animated mesh and we're going to use this to deform another mesh. So I'm going to be using our animated tube to deform this tube over here. The geometry between these can be completely different. I'm not trying to match up the point numbers at all. I could choose to use less rows here, or I could choose to have more rows so I have a better deformation. I'll re-enter the solver. The first mesh will be called animated mesh. I'll get a second FEM solid object node. I'll set this to be our target mesh. Once again, we'll be working in our deformation tab, and here we'll be referring to our second tube. Although I have an issue here, because I have not actually converted this mesh yet. I'll create a null to reference this mesh. This null will be called target mesh. We can now refer to this null, however this will still not work, because once again we are going to require a tetrahedral mesh. This will be set using a tet conform node. For this kind of use case, the default settings are fine. We should now have our solid geometry added to the network, and we can deform this geometry with our animated mesh. I'll merge both my solid geometry nodes together. I'll then set the simulation to read from my output. I can now start working on the settings for the target mesh. So technically, if we added target strength to this mesh, it could be added to the simulation. So I'll give this a target strength, and we'll simulate this. In some cases, it will join the simulation, in some it won't. In this case, we do have an effect. There is a slight effect of the simulation on this mesh. Both meshes will actually affect each other, and this is something which we do not want. So for the mesh that I want to have deformed by another mesh, I'm actually going to set this target strength to be 0. This means that this mesh will have no effect on other meshes. I will also go to the animated mesh, and I'll go to the collisions tab. Here I'm going to turn off all of the collisions on this mesh. If we reset the solver now, neither mesh should have an effect on the other. And this is what we want for our default situation. I can now update the collisions in the target mesh. I'm going to set this mesh so that it collides with itself. This is one of the big advantages we can get off this type of simulation. I can now get these meshes to work with each other. We're going to use an FEM solver for this, and in this case we're going to work with the region constraint node. I'll place the region constraint after my merge node and before my solver. There are two options in this node. We have our container and we have our region. The container will be the object that we are trying to deform, so we'll set the object here to be our target mesh. The region will be the mesh which is deforming our container, and the object here will be set to our animated mesh. Our container is now being animated by our target mesh, but this animation does not look particularly good. To try and improve this, we can raise the target strength. However, this will actually not solve the problem that we've got here. When we look at the target mesh and the input mesh, we can see that the size is actually radically different, and that a lot of the deformation can be contained within the target mesh. If I lower the radius, we should get a slightly better deformation. We're now getting a much better deformation based off the original animation. This may look wrong, but it is actually deforming to our animation. The issue here is actually with the deformation for the animation, in that I've actually lowered the deformation strength here. I need to reset this to be a full strength deformation. We should now have the expected deformation. So you should note that both the deformation strength on the constraint and the target strength on the animated mesh will have an influence on this deformation. The target strength will have a lot of effect on the constraint. But as a general rule, the values that we're going to set here will be very high. So this is how we can use an animated mesh to drive an FEM simulation. This can allow us to get very interesting deformations, especially around the inner corners of a mesh. For example, here we're getting much better compression on the inner corner of this mesh than we would have with the default setup. Using an FEM simulation, we'll get a much better deformation here. This deformation would make this mesh more suited to using further deformations. For example, this would be a major problem area for cross simulation. Our deformed mesh would have far fewer issues here. However, my focus here is primarily on rigging, and what we have done here is the basis of what you need to know to apply this to a rig. We'll start looking at how we can improve this deformation next.